Hello, pre-calculus students. In this video, we're going to do what I hope is a review on complex numbers. Now, complex numbers, all the numbers that we know about in the form a plus bi are complex numbers. Now, we split the complex numbers into two parts, the reals and the imaginaries. So real numbers have b equal to 0. So this is the real part and b is 0. In the imaginaries, b is not 0. Now some people can say the number 2 plus 3i is a complex number, and it is. But so is 6.2. All of these numbers are complex numbers. Now, there are different mathematicians who categorize things a little bit differently. The way I look at it is 2 plus 3i, any number that has a b not equal to 0 is an imaginary number. So 2 plus 3i is an imaginary number. 3i, so that's 0 plus 3i, is pure imaginary. Some people say that this is complex, this is imaginary. Well, I'll agree that this is complex like every other number, but I say this is, if we're a subset of the complex numbers, this is imaginary, and because a is 0, this one is pure imaginary. And I'll go over the rest of these reals in a minute, but when we look at a standard form of an imaginary number of the form a plus bi, a is the real part of the number, b, not bi, but b is the imaginary part. So if a is 0, there's only an imaginary part, so that's purely imaginary. And if b is equal to 0, then there's only a real part. So that, I'm one of the people who thinks that this should be considered imaginary and this should be considered pure imaginary. All righty, let's start with the natural numbers. You never have half of a rock. You got 1 rock, 2 rocks, 3 rocks. So the natural numbers are the counting numbers, 1, 2, 3, etc. Now the whole numbers are all the natural numbers plus 0. So the whole numbers are 0 plus 1 and 2 and 3, etc. Now the integers are the whole numbers, the natural numbers, 0, and the negative natural numbers. So you could think of it as the whole numbers and their negatives. And you can see every whole number is an integer. Every natural number is an integer. Now, if you take 2 integers and divide them, you come up with rational numbers. This is the number 62 divided by 10. And so it's 62 is an integer, 10 is an integer. That's a rational number. -3/4 is a rational number because -3 is an integer, 4 is an integer. But 2 is also a rational number because you could write it as 2 divided by 1. 2 and 1 are both integers. Of course, they're both natural numbers as well, but they are both integers. So all natural numbers are rational numbers. Then any real number that's not rational is irrational. 2 minus √5, square root of 7, pi, e, all of these are irrational numbers, but they're all real. And I've already shown you this. Now you may learn a mathematical shortcut here. IFF, if and only if. In math, we abbreviate if and only if as IFF. If this complex number is equal to this complex number, well, this one is equal to this one if and only if the real parts of the two numbers are equal and the imaginary parts of the two numbers are equal. That's what constitutes equality in complex numbers. When we add and subtract in complex numbers, it's like combining like terms. You combine the real parts together, you combine the imaginary parts together. Here you go, 2 minus 4 is -2, 3 minus 5 is -2, and then of course the i's. When we write imaginary numbers in a+bi form, which is called standard form, adding and subtracting is easy. When we want to multiply, we have to do the FOIL method, which is first, outside, inside, last. And then, after we've done the FOIL method, we combine like terms. We know that I squared is -1 times -2 is 2. Add those, and there's our final answer. When we multiply I together, we keep getting this pattern. We know that a non-zero number to the 0 power is 1. Multiply a constant by I. There's I to the first is I. I squared is I times I. I cubed is I squared times I, which is -I. I to the fourth is I squared times I squared, which is 1. I to the fifth is I to the fourth times I to the first, which is 1 times I, which is I. So we keep getting this repeating pattern of I, -1, -I, 1. So my question, because I'm a good American patriot, is what is I to the 1,776th power? You should be able to figure that out based on this pattern. We'll go over that in class. Now the numbers 3 plus √5 and 3 minus √5 are known as conjugates. There's let's see, we start with the whole number and then you have the irrational part out here. This one is 3 plus the √5 and then the same 3 minus the √5. Those are conjugates. We also have complex conjugates. 3 plus 5i and 3 minus 5i. The 3 doesn't change, just the second one does. And we'll see why that is so handy in a bit. When you multiply complex conjugates, things get pretty easy. Because if you do the FOIL method, see these two middle terms cancel, and you get, this is just kind of like a plus something, a minus something is going to be a squared minus b, b squared, but it's bi squared, or so bi quantity squared, which is b squared. I squared is -1, boom. Multiplying complex conjugates gives you a real number, because you notice there's no i's in here. So x squared plus 4, it's in this format. X is a, b is 2. That means I should be able to factor this to x plus 2y, x minus 2y. I expect that you can FOIL that out and get this. Dividing with dividing complex numbers is not fun when they're written in standard form. So if I want to divide these two numbers, I'm going to multiply top and bottom by the complex conjugate. So this numerator gets multiplied by the complex conjugate of this one, and so does the denominator. And this is just 1, so I'm not changing the value. If I FOIL this out, I get this quantity. This is down here, multiply those together and I get 5, because that's 2 squared minus I squared. Do not leave your answer like this. This is not the form of a complex number. Form of a complex number is a plus bi. There's our final answer. So this equals this. Similarly, over here, you've done this before. 3 divided by root 5. We wanted to get a rational, or we want to get a rational number in the denominators. We multiply top and bottom by root 5. And you get 3 root 5 over 5. Why did we ever do that? Well, because 3 divided by root 5, in the days before a calculator, you had to use a slide rule. You would look up the square root of 5 on a table and you'd have 3 divided by this. That's a long, nasty division problem. We don't want to do that. So it was easier to multiply 2.2361 by 3, because that's a pretty easy calculation, and then dividing that answer by 5, pretty easy calculation. Similarly, if you ever had a problem like this, you multiplied top and bottom of this number by the conjugate of the denominator. So multiplying top and bottom by 3 minus root 5 gave us 9 minus 5, gave us a denominator of 4 over here. So you can see that we've done things like this before in algebra. Now, just to show you, square root of 100, you can multiply that, factor that to square root of 25 times square root of 4. You can see that's 5, that's 2, that's 10. Everything works out pretty. But the square root of negative 25 times the square root of negative 4 is not the square root of 100. Multiplying under the radical works great for real numbers. With imaginary numbers, we have to be a little more careful. The square root of negative 25 is 5i. You factor the square root of negative 1 out, so it becomes 5i. Same here, the negative 4, that becomes 2i when you take the square root of it. So when you multiply this times this, you don't get the square root of 100, you get the negative square root of 100. So my point in showing you this is, when you have negative numbers under the radical, make sure you get those i's out and deal with the i's appropriately. Don't just multiply the numbers under the radical and get a number here. That only works for the real numbers. So that was a fun introduction, reintroduction, review, however it is for you, of complex numbers. Hope you got something out of that. Have a great day.